Hello everyone, welcome to my third video on L'Hopital's rule. So in this video over here, we're going to learn how to solve indeterminate forms of the type infinity minus infinity. Okay, so the strategy to apply here is that we need to reduce it from a case 3, infinity minus infinity indeterminate form, down to either a case 2 or a case 1. We saw in the previous video that a case 2 indeterminate form is 0 times plus or minus infinity, where we have to apply the flip strategy. So you're either going to reduce it down to a case 3 then to a case 2, and then from a case 2 down to a case 1, which is a 0 over 0 or infinity minus infinity. Remember, for L'Hopital's rule, we have to get 0 over 0 or infinity minus infinity. So you might have to reduce it down from a case 3 to a case 2, then from a case 2 to the case 1, or you may be able to, depending on the strategy that you use, you might be able to simplify it from a case 3 straight away down to a case 1. And how are we going to do this? We're going to simplify. Okay. So simplifying this means that you might have to use factoring techniques. You might have to use the multiplying by the conjugate technique. If you have a square root, you're looking out for that. You might have to use log or trig properties. And finally, you might have to find a common denominator. If you're dealing with fractions, finding a common denominator is the way to go. So let's look at a couple of practice problems and apply our strategies. Note that there's other simplifying techniques that may have to be applied depending on the problem. So every situation is different, and we're going to look at a couple of examples. Let's go ahead and do that. So in this first example over here, we have to use L'Hopital's rule to evaluate the limit, and the limit that's given is limit as x tends to infinity of x minus x times e to the 1 over x. So let's go ahead and solve that. We start off by substituting x with infinity. So here on the left hand side, it's just infinity minus infinity times e to the 1 over infinity. 1 over infinity is 0, and e to the 0 is 1. So what we really have here is infinity minus infinity. So this is the first time we see this indeterminate form, infinity minus infinity. How do we proceed? How do we solve this? So pause the video, try to see if you could maybe simplify this, rework it, try to change the way it looks. It may not be obvious, but the first thing that I see is that both terms have an x. So the first thing I'm tempted to do is GCF. Find the greatest common factor. We could factor out an x. So I'm going to go ahead and do that. Limit as x tends to infinity. I factor out an x, and we have 1 minus e to the 1 over x. Okay. Why? What does that change? Well, now we have a multiplication. And if I substitute x with infinity, we have on the outside here infinity, and we have on the inside here e to the 1 over infinity. 1 over infinity we said was 0, e to the 0 is 1, and we have 1 minus 1, which is 0, which gives infinity times 0. We reduced it down to a case 2. So we're dealing with the indeterminate form. We said infinity times 0. So that means we have to flip one of these guys. Which one do we flip? Do we flip the x, or do we flip what's in the bracket? Well, my game plan, I'm going to flip the x. So this is equal to the limit as x goes to infinity of 1 minus e to the 1 over x to the negative 1. Okay. Now if we plug in infinity with x, we get e to the 1 over infinity, which is 0. E to the 0 is 1. 1 minus 1 is 0. And on the bottom we have 1 over infinity, which is 0. So this gives us L'Hopital's rule. So we could apply L'Hopital's rule with the indeterminate form 0 over 0. So now we reduced it down to a case 1. You might have been tempted to drop the 1 minus e to the 1 over x. If that works, you could do that. That's not the way I'm seeing it. So I'm going with this method instead. So this says now we could take the derivative of the top and bottom individually. So we have the limit as x goes to infinity. The derivative of the top is, well, the derivative of 1 is 0, so that's gone. The derivative of e, we could think of this as, I don't know if this is easier, but instead of thinking of it as 1 over x, we could think of it x to the negative 1. The derivative of negative e to the x to the negative 1 is negative e to the x negative 1. It stays the same. And then multiply by the derivative of what's in the exponent. So the derivative of what's in the exponent is times negative 1 x to the negative 2. Okay, so we just apply power rule, drop the exponent, the negative 1 comes in the front, and the exponent, you subtract 1 in the exponent, giving us negative 2. Okay, and on the bottom, what do we get? We get negative 1 x to the negative 2. And now you can see why this works, because x to the negative 2 here and x to the negative 2, they cancel, leaving us with just limit as x goes to infinity, and we're left with negative e to the x to the negative 1. And now if we substitute infinity into the x, we get negative e to the, we could rewrite this as, bring it back as 1 over x. So this is 1 over infinity, negative e to the 0, and this is just negative 1. So this limit over here is actually negative 1. So again, infinity minus infinity, which goes to infinity faster, the left side or the right side? We don't know. In this specific case, when you subtract the two terms that take off to infinity, we actually get a finite value, negative 1. Okay. So let's look at the next example. So in this example over here, again, you use L'Hopital's rule to evaluate the limit, and the limit that's given is limit as x tends to 1 from the positive side of 1 over x minus 1 minus 2 over x squared minus 1. So pause the video, try this on your own, see if you can get it. The first thing we do is substitute our x with 1. So we get 1 over 1 minus 1, which is 1 over 0. So this is infinity. And here if we substitute 1 squared minus 1 is 0. 2 over 0 is infinity. So infinity minus infinity. Okay, so we have a case 3 L'Hopital's rule. Let's go ahead and try to reduce it. So here, what's your game plan to reduce? The thing that I'm seeing to find a common denominator. We have a fraction here and a fraction here. We have a difference of two fractions. Find the common denominator. I think that's the way to go. So here we have x minus 1. Here we have x squared minus 1. X squared minus 1, you can think of it as x plus 1, x minus 1. Difference of squares. So since x squared minus 1 is x plus 1, x minus 1, the only thing that's missing on the left hand side is to multiply the x plus 1 on the top and the bottom. So let's go ahead and do that. This gives us the limit as x tends to 1 from the positive side. We have x plus 1 over x squared minus 1 minus 2 over x squared minus 1. Okay, so I multiplied the top and the bottom by x plus 1, giving me x plus 1 on the top, and on the bottom x minus 1 times x plus 1 is x squared minus 1. So they have the same base. Okay, this doesn't really help, but since they have the same denominator, we could add the numerator. So, or in this case, subtract the numerator. So x plus 1 minus 2 gives us the limit as x tends to 1 from the positive side. We get x minus 1 over x squared minus 1. Okay. So at this stage here, we reduced it down to L'Hopital's rule. We have 0 over 0. But since we're here, if you want to apply L'Hopital's rule, you could. But at the same time, you could just factor the bottom and cancel out the x minus 1s, because x squared minus 1 from difference of squares is this. So we could rewrite this as x minus 1, x plus 1, and the x minus 1s cancel, and we're done. But since it's saying specifically to use L'Hopital's rule, let's go ahead and apply L'Hopital's rule in this case. So both methods would work. Here we get the indeterminate form 0 over 0. So take the derivative of the top. We get 1, and take the derivative of the bottom, we get 2x. And substituting the x with 1, we get 1 over 2. And this is the answer. Okay. And notice if you would have factored out, like method 2, let's say, if you would have factored the x squared minus 1, you would have got the limit as x tends to 1 from the positive side of x minus 1 over x minus 1 times x plus 1. And notice that the x minus 1s would have cancelled, leaving you with 1 over x plus 1. And if you substitute the 1, you get 1 over 2. Okay. So whichever way you did it, you got the same answer. The answer is a half. Okay. So let's keep practicing. So in this next example, example number 3, we have to use L'Hopital's rule to evaluate the limit. And the limit that's given is the limit as x tends to infinity of x minus square root of x squared minus 1. So let's go ahead and solve this. So first of all, we begin by substituting x with infinity. We get infinity minus infinity squared is infinity, minus 1 is still infinity, and if you take the square root of infinity, it's still infinity. So we get infinity minus infinity. So we're dealing with a case 3 L'Hopital's rule problem. So how do we simplify this? Well, I see a square root, so my first instinct is to multiply by the conjugate. Let's go ahead and try that. So I'm going to just erase this. And we're going to multiply the top and the bottom by the exact same thing, but we just switch the sign over here. Do not switch the sign of what's inside the square root, okay? It's the two terms, what's in between the two terms. So instead of x minus square root of x squared minus 1, it's going to be x plus square root x squared minus 1, okay? Over the same thing, x plus square root x squared minus 1. And solving this, we get limit as x tends to infinity. We're going to multiply x times x. This is a binomial. So x times x, we're foiling, giving us x squared. Then here we get x times square root of x squared minus 1. Then we get negative x times square root of x squared minus 1. Notice these two terms are always going to be the same, opposite sign. So these will always cancel. And then lastly, we get negative square root of x squared minus 1 times the square root of x squared minus 1, giving us negative x squared minus 1. The square roots essentially just cancel. Okay, all this over x plus square root x squared minus 1. Okay, so the next thing, since this, if we focus on the numerator, notice that these terms canceled and we have a negative in brackets x squared minus 1. We distribute the negative, giving us x squared minus x squared plus 1. So the x squareds cancel because they're the same term, opposite sign, and we're left with a positive 1 on top. So we get positive 1 over x plus square root of x squared minus 1. And this is very nice because we have a number on the top, on the numerator, meaning that we will never get an indeterminate form here because it's not going to be 0 over 0 or infinity over infinity. So we're actually done. We do not have to apply L'Hopital's rule in this case. Multiplying by the conjugate gave us an opportunity to solve it without L'Hopital's rule. Okay, so replacing your x with infinity here, this denominator goes to infinity, so you get 1 over infinity, which we know is 0. And that's the final answer. We're done. Okay. So let's take a look at another example. So in this next example, example number 4, it says to use L'Hopital's rule to evaluate the following limit, and the limit that's given is the limit as x tends to 0 from the positive side of cosecant x minus cotangent x. Again, pause the video, try to solve this on your own, see if you're able to solve it. So we begin by evaluating the limit. So if we substitute 0 into cosecant, well, just remember, cosecant is 1 over sine, and cotangent is 1 over tan. If you substitute 0 into the sine, you get sine of 0, which is 0, or a number that's very close to 0, and 1 divided by 0 is infinity. Similarly for the tan, if you plug in tan of 0, or a number that's very close to 0, this is 0, and you have 1 divided by 0, or a number that's very small. So if you divide any number by a number that's extremely small, the entire number gets big, it explodes to infinity. So we have the indeterminate form, infinity minus infinity. Case 3. Let's go ahead and simplify it. So in this case here, we have trig formulas. So as we just saw, we could rewrite cosecant and cotangent as 1 over sine and 1 over tan. So let's go ahead and do that. So I'm going to rewrite this as the limit as x tends to 0 from the positive side of 1 over sine of x minus 1 over tan of x. There may be other ways to solve this, but this is just the way I'm seeing it now. So now we have a fraction. We have two fractions separated by a subtraction sign. How do we deal with this? Well, we find a common denominator. So I'm going to multiply by tan, and then multiply by sine, and then multiply sine and tan. So really what we're doing is a over b plus minus, c over d is equal to a times d plus minus, it doesn't matter if you have an addition or a subtraction, b times c over b times d. So this is the formula that I'm using. This is always a general formula to find the common denominator. Whenever you're adding or subtracting fractions, you can just apply this. And that's what I'm going to do here. So this gives us tan x. Oops. Don't forget to write your limit. That's a mistake. So we have the limit first as x tends to 0 from the positive side. And now we have tan x minus sine x over sine times tan. Okay. And now we have our fraction. And if we substitute 0 at this stage, we get tan of 0, which is 0, sine of 0, which is 0, 0 minus 0, we get 0 on top. And if we substitute 0, we get sine of 0, and 0 times tan of 0, which is 0, is 0. So we have the indeterminate form 0 over 0 here. So we reduced it down to a case 1, so we could apply L'Hopital's rule. Let's go ahead and do that. So we have the limit as x tends to 0 from the positive side, and we're taking the derivative of the numerator on its own and the denominator on its own. The derivative of tan on the numerator is secant squared, and the derivative of sine is cos, so minus cos. on the bottom we have sine times tan. So if you said that the derivative is cos times secant squared, that's incorrect. Be careful, we have a multiplication of two functions here. What do we have to use? Product rule. So don't forget our derivative rules still apply here, okay? So here we have to apply product rule. So recall, product rule is f times g prime is the derivative of the first times the second plus the derivative of the second times the first. Let's go ahead and do that. The derivative of sine is cos, we leave the tan, so cos times tan, plus, because it's product rule, and now derivative of tan is secant squared, x times, we leave the sine. Okay, so we have to apply product rule. So next we evaluate the limit. If we substitute x with 0, we get secant squared of 0, which is 1, and cos of 0, which is 1. 1 minus 1 is 0. We get 0 on the top. And here there's a tan, so tan of 0 is 0, canceling this whole term. And here there's a sine, so sine of 0 is 0, canceling out this whole term. So here we have, again, L'Hopital's rule, the case 0 over 0. We apply L'Hopital's rule once more. 0 over 0. So let's take the derivative of the numerator. The derivative of secant squared is, we think of it as secant x all that squared. And we apply chain rule. So we're going to drop the exponent 2. So we get 2 times secant. So we just drop the 2, subtract the exponent by 1. And now we have to take the derivative of the inside, chain rule. So the derivative of secant is secant tan. So we're going to have another secant, so I'm going to put secant squared, and then times tan. Okay. The derivative of cos is negative sine. Since there's a negative over here, it becomes plus sine. So the numerator is done. Now let's do the denominator. The denominator has two product rules. So let's go ahead and do that. So the first one here is cos times tan. So the derivative of cos is negative sine times tan, we leave, plus now the derivative of tan is secant squared times cos, which we leave. So the first product rule is done. Now we have to do the second product rule. It's separated by a plus, we put a plus. And now the derivative of secant squared, we just saw it, so it's 2 secant squared, exactly what we have here, 2 secant squared x times tan x. And now we leave the sine, times sine, plus, I don't have room, so I'm just going to write down here, derivative of sine is cos, and we leave the secant squared. So now we reevaluate the limit, substitute x's with zeros. Here on the numerator, there's a tan, so tan of 0 is 0, so it's going to cancel out this whole first term, and plus sine of 0, this is 0. So I'm just going to write it up here. The top was 0, and what do we get on the bottom? Well, on the bottom, this term here has a tan, this is 0. Sine of 0 times tan of 0 is 0. Secant squared x, cos squared x. Secant squared of 0 is 1, and cos of 0 is 1. This term here is equal to 1. This term here has a tan of x, so the whole thing is 0. And this term here is also cos of 0 times secant squared of 0 is also 1. So we get 0 plus 1 plus 0 plus 1, which is 2. So we get 0 over 2. Thankfully, it's not an indeterminate form. We don't have to take the derivative another time. We're done. We have a number. 0 divided by 2 is 0, and we are finished. This is the answer. So in our final example here, we're using L'Hopital's rule to evaluate the limit, and the limit is as x tends to 1 from the positive side of 1 over ln of x minus x over x minus 1. So let's go ahead and solve this. Again, I always urge you, pause the video, try to solve this on your own. Watching someone else do math doesn't help you. You really have to take initiative, write it down, see where you get stuck, and then improve. Okay, so make sure you're actually solving these problems on your own. So we have a fraction. The fact that we have a fraction, I'm thinking of finding a common denominator. So let's go ahead and do that. So I'm going to multiply the left side on the top and the bottom by x minus 1, and I'm going to multiply the right side of the equation by ln of x and ln of x. Okay. Well, first of all, we have to ensure that this is in fact an indeterminate form. So substituting x with 1, we get ln of 1 from the positive side, it's 1 over 0, this is infinity, minus 1 over 1 minus 1, yeah, so it's infinity minus infinity. So you should always check this first before you start simplifying, okay? So make sure you do in fact have an indeterminate form, Okay, now that we have an indeterminate form, we're going to reduce it down. This is case 3. We're going to reduce it down to a case 2 or case 1 by finding a common denominator. So we get the limit as x tends to 1 from the positive side, x minus 1 minus x ln of x. All this over ln of x times x minus 1. Okay. So essentially the property that I'm using is always a over b plus or minus c over d. It's just a times d, depending on whether you're adding or subtracting, plus minus c times b, c, over b times d. So this is the property that I'm applying to obtain this from this. This is your a, this is your b, this is your c, this is your d, and this is what you get. Okay. So now we have our fraction. If we substitute 1 into the numerator and denominator, what do we get? We get 1 minus 1, which is 0, minus 1 times ln of 1 is 0, and ln of 1 is 0. Okay. So we have reduced it down to a case 1, L'Hopital's rule. So we could apply L'Hopital's since we have the indeterminate form 0 over 0, which means that we could start taking the derivative of the top and the bottom individually. Let's do that. We take the limit as x tends to 1 from the positive side. The derivative of x is 1. The derivative of negative 1 is 0, that's gone, minus the derivative of x times ln of x. So I'm dealing with the negative on its own, so I'm putting it, and x times ln of x is a multiplication, so we have to apply product rule. So the derivative of x, I'm going to put this all in bracket. The derivative of x is 1. We leave the second function. Not minus, it's a plus because it's product rule. The derivative of ln of x is 1 over x, and we're going to leave the first function. So x times 1 over x. Okay, so that's the derivative of the top. Let's take the derivative of the bottom. Again, the bottom is a product rule. We have ln of x times x minus 1. So derivative of the first function is 1 over x. Leave the second function, x minus 1, plus the derivative of the second function is just 1, and we leave the second function, ln of x. Okay, so let's go ahead and simplify this. Notice here we have x times 1 over x, so that's just 1. X over x cancel each other, so this is just 1. And we have a negative in the front that's going to distribute. So limit as x tends to 1 from the positive side. 1 minus ln of x minus 1, so the 1's cancel, because this becomes negative when you distribute the negative 1. So we're left with negative ln of x on top. Okay. And on the bottom, what do we have? If I distribute the 1 over x, we get 1 minus 1 over x plus ln of x. Okay. So I simply just distributed the 1 over x. So 1 over x times x is 1. 1 over x times negative 1 is just negative 1 over x. And then we have the plus ln of x over here. Okay. Substituting the 1 back in, what we get is on the top is negative ln of 1, which is 0. 1 minus 1 over 1 is 0 plus ln of 1, which is 0. So we could apply L'Hopital's rule once more because we have the indeterminate form 0 over 0. So let's keep going. The derivative of ln of x, or negative ln of x, is negative 1 over x. This is reassuring because it got rid of my ln of x, so I'm feeling confident now. The derivative of 1 is 0, that's gone. The derivative of negative 1 over x, we could think of this as x to the minus 1 just to make it simpler. And instead of applying quotient rule, we're going to apply power rule. So we drop the negative 1. So two negatives become a positive. And then we subtract 1 in the exponent. So we get 1 times x to the negative 2. And the derivative of ln of x is plus 1 over x. Okay. So we're left with this over here. The x to the negative 2 can be rewritten as 1 over x squared. So what we have on the denominator is 1 over x squared plus 1 over x. Okay, and now we could simplify this. So on the bottom we could find a common denominator. We could rewrite this as 1 over x, multiplying the right side by x squared, by x, gives us limit as x tends to 1 from the positive side. On the top we have negative 1 over x, I'm going to leave it like that. On the bottom I'm going to multiply the right hand side by x, giving us 1 plus x over x squared. Okay, so I multiply the top and the bottom by x, so we have x plus 1, and on the bottom they're x squareds. Okay, the reason why I'm doing this is because we have a fraction over a fraction, and now we can multiply by the reciprocal. So I'm not applying L'Hopital's rule yet, I'm simplifying before I use L'Hopital's rule. So simplifying this, I could flip it. I get negative 1 over x times x squared over 1 plus x. Let's put this in brackets. Notice that one of these x's cancels with one of these, and we're left with this. Substituting your x with 1, I mean, you could have substituted at this stage here with 1, that would have been fine as well, instead of doing all this work, but it doesn't really matter. Yeah, it would have been faster just to directly substitute at this stage. Replacing your x with 1, you get negative 1 on top, 1 plus 1 on the bottom, so negative 1 over 2. So the answer is negative a half, and we're done. Okay, so I hope this helped. I hope you keep practicing, and I'll see you in the next video.